This is K.Priyanka from Vijayapatna University of Technology. I'm going to present my internship project on AV dashboard and ADAS warning system at MTech. So, what is EV and ADAS dashboard? Electric vehicle is a digital display that shows important vehicle information such as speed, battery level, driving range, charging status, temperature, and warning messages. What is ADAS warning system? A safety system that detects potential hazards, uh, alerts the driver using warnings like lane, departure, collision, blind spot, and pedestrian detection to prevent accidents. Then, what are the challenges that we used to face? Like modern EVs generate a large amount of real time sensor data. Monitoring multiple vehicle parameters manually is difficult, and critical safety events such as collisions, blind spots, and system defaults can go unnoticed. So, the purpose solution is live monitoring of vehicle parameters using real time EV dashboard and ADAS monitoring to avoid collision through collision warning, blind spot detection, and time to collision. Then, what this project builds. Here, the slide shows the overall data flow of our EV dashboard and ADAS system. First, the sensor ADC and SC SR04 ultrasonic sensor collect data from the vehicle. This data is processed by the EV control module, which updates every 10 milliseconds. Next, the ADAS and fault module, running every 10 milliseconds, checks obstacle distance and detects faults. Then the process information is sent through the UART communication interface to the PC. And finally, the Python dashboard displays the vehicle data, ADAS warning, and fault status in real time. Then, then what are the tools used? STM32Cube was used to write the logics, firmware development, peripheral configuration, flashing the blue pill board. And Pixim Lab. It is a virtual hardware simulator standing in for sensors, LEDs, buzzers, and terminal. No physical wiring is required here. Then Python powers the PC side EV ADAS dashboard, reading live telemetry over the serial link. Then VSP and Teraterm. Visual Serial Port Emulator paired with Teraterm for raw terminal monitoring and shell commands. In Teraterms, by giving the help command, we can get the command list and we can do according to our needs. Here, as I said, this first the STM32, that is ADC plus SCSR04, sends a 10 microsecond trigger pulse to the sensor. The sensor transmits ultrasonic waves and waits for the echo to return. The echo pulse width is measured using timer 2. The distance is calculated using timer 2. And the data is processed by the EV control module, which updates every 10 milliseconds. Then comes the GPIO and ADC. Here, PA0 is used for accelerator pedal, PA1 is used for brake pedal, PA2 is used for SOC seat, PA3 is used for motor temperature. And in digital I/O GPIO-B, PB0 or PB1 is used for front sensor trigger or echo. PB2 or PB3 are used for left sensor trigger or echo. PB4 or PB5 are used for right sensor trigger or echo. PB8 is used for LED collision warning. PB9 or 10 is used for LED blind spot left or right. PB11 is used for LED fault active. Ultrasonic driver. Trigger sensor with a It's a trigger sensor with a 10 microsecond pulse. It measures echo time using timer 2. It calculates the distance from the echo time. It reads sensor one by one to avoid crosstalk. Then it uses a timeout for reliable operation. Here, speed, power, and state of charge. This slide explains the vehicle dynamics model used in our EV simulation. The system calculates the vehicle speed based on motor torque and drag. Then it calculates the power consumed by the motor. Based on the power consumption, the battery state of charge decreases over time. Finally, the system estimates the remaining driving range and monitors the motor temperature to simulate realistic EV behavior. Then comes the collision warning (TTC) and blind spot logic. Here TTC predicts how soon a collision may happen. Collision warning gives warning or critical alerts based on distance or time to collision. Blind spot detection warns if a vehicle is beside the EV. Overspeed warning alerts the driver when the speed exceeds the time limit. Fault detection. This slide explains the faults handling and communication system. The system continuously monitors faults such as motor overheating, low battery SOC, and collision detection. If any fault occurs, the system enters a safe fault state to prevent damage. The UART command shell allows user to send commands and monitor the system through serial communication. Finally, all vehicle data, fault status, battery level, and speed and ADAS warnings are displayed in real time on the Python dashboard. So PPT is this much. Now let me show you the STM32 CubeID codes. So here comes the codes. Yeah, many header file and source files are there to keep it in a modular form. Then main.sit. Here initialization of STM32 peripherals is done using UART and GPIO. Sensor values are processed and transmitted through UART. Then evcontrol.c. Module is responsible for EV parameters, torque, battery charge, and motor temperature. Then, then different ultrasonic.c. It handles the 3SC SR04 ultrasonic sensors and for ultrasonic detects in front, left, and right. Then like ADAS.c, ADAS.h, it implements driver's assistance logic, blind spot, and alarm systems. Then Fall.c and Fall.h. They are used for fault register and generation based on UART and detected conditions. Then UART shell.c and UART.shell.h. These formats are EV and ADAS parameters that converts them into a serial data packet and sets into Python dashboard theory through UART communication. Now let me show you Pixim Lab in which we did the simulation. See, here we can do the reset. Now going to the spare parts. Here acceleration pedal is connected to PA0, brake pedal is connected to PA1, SOC is connected to PA2, and motor temperature is connected to PA3. It is the virtual terminal that displays all the outputs. It is for the front, and this ultrasonic sensor is for left, this is for the right, and this is called the potentiometers. And here several LEDs are connected for different display. Like if the motor rises to the top, here fault alarm blows. Here we can see the output of the virtual terminal. Here SOC is 40.0, front is 242, L is 40. Collision, you can say it. Similarly, it can also be seen in Teraterm, but unfortunately, the Teraterm is not working properly. The command is not working properly. That's why I could not show. Now coming to our elect let me show you a demo. So this is our final project. It is the speedometer that tells us the speed of the vehicle. This graph tells us about the speed history. This is the battery of the vehicle. And here you can see alarm. It is saying non. It also has advisory and critical alarms. Then it tells us about the torque, that is, that changes according to the vehicle, acceleration, brake, and here motor temperature, alarm, fault, signal. Signal is on, alarm is on advisory mode. Here first vehicle is at 20 centimeter distance. Here we can see another vehicle is at 67 and another one is at 96. This is the ADAS bird eye view, and it is the battery range, and this is known as EV matrix. So this is all about my project. Thank you so much.